All right, welcome to this week's discussion hour talk. Thanks for joining us. This week we'll hear from Heather Shaddox. She is a graduate student in the University of Santa Cruz Seismology Lab, and she studies transient slow slip earthquakes as well as the seismic detection of oceanic internal waves. And I think the former will be the focus of our talk today, so I'll let her take it away. Here's Heather.
Thank you. And okay, does that look all right?
Yes, it does.
Awesome. Okay. Well, yeah. Thanks so much for inviting me and for everyone who showed up. Today, I'm talking about work with Susan Schwartz, as well as some work with our collaborator Noel Bartlow, where we have found burst type repeating earthquakes related to transient slow slip. And we think that they're actually driven by transient slow slip. And because of this, we think they can be a pretty useful proxy, at least in some environments, for slow slip transients. Now, to give some background, I'm sure this is going to be, review for a lot of you, but just in case, slip-on faults occurs as a spectrum from slow continuous sliding, which is aseismic, to, rapid slip during earthquakes, which of course is seismic. And within this spectrum, you have the transient release of stress through aseismic or slow slip, which I'm going to broadly call here, just slow slip transients. And a really well-studied form of slow slip transients are slow slip events in subduction zones. And here's a cartoon of a subduction zone. And I have labeled on here where we have slow slip. You can have shallow slow slip, which is often offshore, up dip of the seismogenic zone shown here in red, as well as deep slow slip events down dip of the locked megathrust. And slow slip events are similar to earthquakes in that there's a period of locking where stress is accumulated and then a period of release. And the release occurs slowly over days, weeks, months, even years, versus in earthquakes where it happens rapidly over seconds to minutes. And in general, transient slow slip can be spontaneous or even episodic, like slow slip events, but slow slip transients can also be triggered either by earthquakes, and if this happens on adjacent segments of the fault, we call this afterslip. It can also be triggered by fluids or at least a change in pore fluid pressure. Now, slow slip events and slow slip transients are aseismic. They're too slow to generate seismic waves, so we traditionally detect them with geodesy, often land GPS stations. But for shallow slow slip events, they're often located far offshore, out of the range of land GPS, which makes them difficult to detect. But if we have ocean bottom instrumentation, on the sea floor above the portion of the plate interface that's failing in these slow slip events, then that increases detection capability. But even for, slow slip transients on continental strike slip faults, beneath land, if they're relatively deep and small, they're still difficult to detect. And so, we often use related microseismicity to indirectly detect slow slip transients. And the most well-studied form of microseismicity related to transient slow slip are tremor and low frequency earthquakes. So tremor is a weak, extended duration seismic signal that often looks like noise on seismometers. And tremor's been, really well spatially and temporally correlated with slow slip events. And tremor's thought to be made up of repeating low frequency earthquakes or LFEs. They're called low frequency earthquakes because they're depleted in high frequencies for their size, and they're thought to be little locked asperities that are driven to failure by the plate around them slipping aseismically. And here's some in-member models for how LFEs within families fail. This is from Chesler and Kreger in 2017. And so one idea is that you have the entire patch for an LFE family slipping the exact same way and the same asperity every time. But if you look in detail at LFEs within families, they have a range of magnitudes and they occur in clusters that are irregularly spaced in time. So it's unlikely that it's the exact same asperity that's failing every time. It's more likely to be one of these two models. So there's a connected patch model where the same, family kind of patch is the same, but each LFE is rupturing a subpatch, and in this case, they're connected. There's also a model where you have the same, once again, family patch, and within that patch, there are distinct LFE asperities that are rupturing separately and they're not connected. And in reality, it's probably something in between these two models. So With that background in mind, the key questions I'm going to kind of talk about today, or I have today, are how we can improve the detection and location of transient slow slip, especially when we don't have, we don't have nearby, or if it's out of the range of like GPS stations, for example, and if we don't have tremor. So if there's non-tremorgenic areas and we can't use that as a seismic proxy, how can we still improve the detection of transient slow slip? And ultimately, what can we learn about the interplay of seismic and aseismic slip if we can detect a lot of really small slow slip transients? And the interplay of seismic and aseismic slip is important to study and understand for many reasons, but especially in terms of seismic hazard, because slow slip events can precede or even trigger large damaging earthquakes. And also, if the more stress that's released aseismically on a fault, the less stress is available to fail in a large earthquake. So, slow slip can also decrease seismic hazard. So in terms of hazard, it's really important to understand the interplay of seismic and aseismic slip. Okay. So now I'm going to move on to a different form of seismicity that's related to, in general, slow slip. So I'm going to talk about, repeating earthquakes. This is the classic kind of continual type repeating earthquakes, which are events with nearly identical waveforms thought to repeatedly rupture the same way in the same location. And the idea is that you have a seismic asperity, or a little, locked, stuck patch on an otherwise aseismically slipping fault. And the patch is stuck, but it's being loaded by the plate around it. And eventually this patch will rupture and catch up with the plate rate. This will happen repeatedly. There'll be repeating earthquakes. Now, these are loaded continually by, pretty continuous creep or aseismic slip just from tectonic loading. And so they have pretty regular repeat intervals and magnitudes. Now, I'm going to mostly focus on a different kind of repeating earthquake, or kind of classification, which are called burst type repeating earthquakes, which have really similar waveforms. But they're called burst type because they're concentrated in time, and they also have short and irregular repeat intervals and variable magnitude. So they are not loaded by continuous creep or tectonic loading. Instead, we see them associated with afterslip following large earthquakes, which is a form of triggered, transient slow slip. And because of this, we think that they can be used to identify and locate transient slow slip. Now, to give a bit more detail on what we're thinking of when we say, when we talk about burst type repeating earthquake families, we actually think it's similar to repeating low frequency earthquakes that I talked about before with this model here. So, it's likely that we have, for a burst type repeating earthquake family, one kind of main family patch, and each burst type repeating earthquake in that family is likely rupturing, a sub patch. And they could be, possibly overlapping, but we think that it's unlikely that it's the exact same asperity. But the key here is that we still think that they're driven to failure by transient slow slip. And so they can be used to identify and locate slow slip transients. So I'm going to study this in more detail, or at least, present this in more detail for two different study areas today. The first one at the Northern Hikurangi Margin in New Zealand, which I think a lot of the audience is familiar with, specifically during a slow slip event that occurred in 2014 that was detected really well with ocean bottom instrumentation. And the second area is the Anza segment of the San Jacinto Fault Zone in Southern California. So we wanted to, kind of look at burst type repeating earthquakes in a continental, strike slip setting. And this area was great because of the instrumentation. There are 4 borehole strain meters near our study area, and so really small, strain changes can be detected, and therefore, small, deep slow slip transients. And there's also an excellent earthquake catalog here, which makes, studying the seismicity fairly easy, straightforward at least. All right, so the first study area is at the Northern Hikurangi Margin. And the main questions here are whether we can find burst type repeating earthquakes related to a shallow offshore slow slip event. And kind of secondary specific to this area is what's the relationship between subducting oceanic relief, shallow slow slip events, fluids, and microseismicity here. Right. So here's the North Island of New Zealand. Here's the Hikurangi Margin, where the Pacific plate subducts beneath the Australian plate at a rate of about 4.5 centimeters a year. And the incoming Pacific plate, I want to point out, is the Hikurangi Plateau, and there are a lot of seamounts. So this is a pretty rough incoming plate. And there have been deep slow slip events detected, greater than about 30 kilometers, as well as shallow, mostly offshore slow slip events. I'm going to focus here at the northern margin. So here we are offshore of Gisborne here. And in this area, there have been subducted seamounts shown here in gray imaged. And down dip of these seamounts, also imaged have been these high reflectivity zones near the plate interface that are potentially fluid enriched sediments that were entrained with seamount subduction. And these areas have been broadly correlated with where we have these shallow offshore slow slip events. So there's this interesting relationship of seamount subduction, potentially fluids, maybe fluid overpressures, slow slip events, and then I'm really interested to see how seismicity comes into play here. And we're able to study that because the Hikurangi Ocean Bottom Investigation of Tremor and Slow Slip, or the Hobbits experiment, deployed 24 absolute pressure gauges, shown here as these yellow squares, and 15 ocean bottom seismometers, which are shown as these blue inverted triangles, offshore of Gisborne between May 2014 and June 2015, in the hopes of recording a shallow offshore slow slip event. And the experiment was successful. So there was a 2 to 3 week magnitude 6.8 slow slip event between September and October 2014 that was, recorded and modeled using both land GPS, but as well as these offshore absolute pressure gauges. And the contours of slow slip are shown here in millimeters of slow slip, and this is in Laura Wallace's 2016 paper. Now you'll notice that in gray here, this is one of the subducted seamounts I showed on the last slide. So we have this really well recorded slow slip event, we have the seamount here, and we have this array of ocean bottom seismometers, which really leads me to the question of what's going on with the seismicity and how does it relate. Okay. So Erin Todd, so former, she did her PhD at UC Santa Cruz as well. She created a catalog of earthquakes between September and October of 2014. So she really looked before, during, and after the slow slip event. And she found an increase in seismicity towards the end and after the slow slip event. And most of these earthquakes are co-located with this subducted seamount shown here. So mostly towards the end and after the slow slip event and at the seamount. She also found detected tremor, offshore tremor, using the OBS, or the ocean bottom seismometers. And similar to the seismicity, she found a lot of the tremor after the slow slip event, or at least towards the end and after, mostly at the subducted seamount. So keep that in mind. Now I'm going to talk about how where I came into the picture looking for repeating earthquakes. So to look for repeating earthquakes, I used template matching, where you essentially start with a template. In my case, it was just a waveform, and you compute cross correlations with continuous waveform data, because you're really just, in my case, I'm looking for very similar waveforms. And so if it has a high correlation, those could be repeating. And I selected templates from Erin Todd's catalog and also from Jefferson Yarse's catalog. So he made a catalog using the OBS and land, seismic stations throughout the entire deployment period from May 2014 to the end of June 2015. And I relocated these events using GrowClust, which is just a relative relocation algorithm. And if there were events that were in the general area of slow slip and within 5 kilometers of the plate interface, because we were really interested in activity near the slow slip event on the plate interface, we selected them as templates. And so we ended up with 123 templates total. Now, here's all the seismicity during this time period. There's obviously a lot, but there was not a lot, on the plate interface near the slow slip event. So here's this cross section A to A prime. That's what's shown here. I have this red dashed line is, roughly the plate interface, and there's not a lot of plate interface seismicity, and the stars are what I ended up using as templates. So really what sticks out is this area here, which is actually near the subducted seamount that I'll talk about later. So once I selected templates, I then used EQ Core Scan, which is an open source Python package to perform template matching. And we ran these through the entire deployment period, used a couple different template lengths, and we ended up saying that if there was a correlation coefficient of an average correlation coefficient of 0.95 at a minimum of 3 of the OBS stations, we called this a repeating earthquake candidate. So really similar event, at least within our bandpass. And using this criteria, we do find repeating earthquakes. We found 78 repeating earthquakes within 29 families. And here are 2 sample detections. In red, this is a template event, and it's overlain its repeating earthquake detection in black. So visually, you can see how similar these are. And in terms of where they're located, well, repeating the large stars on this figure are, repeating earthquake families. And so most of them are located here, kind of at the down dip edge of the subducted seamount. And they're colored according to time, or at least the timing of the first event in the family, with the timing of the slow slip event shown here. So most of them are about at this time period. So really, after the slow slip event, similar to the tremor, which is also plotted here as these small circles, also colored by time. So now we looked kind of in space where these repeating earthquakes were located. Now let's look a bit more at time. So on this top panel here, these are all the template events that we used from with x-axis just being time and the y-axis local magnitude, and the slow slip event timing shown here in gray. And the red events are templates that actually found detections. And then panel B here are all of the templates that found detections shown here in red and the detections they found. So these are all of the repeating earthquake families, and they're colored according to family. And what really pops out is after the slow slip event, there's a concentration in repeating earthquake activity, and most of this is at the subducted seamount. So the bottom panel here is really just zooming in on the repeating earthquakes at the seamount. And it's more clear that it's towards the end of the slow slip event, continuing up to 7 weeks after we have this activity. And within families, there are these varying magnitudes in short and irregular repeat intervals, which makes them burst type repeating earthquakes, which have been associated with afterslip or transient slow slip. So we have these burst type repeating earthquakes, we have increase in microseismicity, we have tremor, all after the slow slip event at the subducted seamount. So of course the question is, what's happening at the seamount? And luckily, there's a seismic reflection profile that crosses the seamount, which is shown on this map here. This is 05CM-04, and this figure we modified from Barker et al. In 2018 to show, to really just plot our repeating earthquake, the burst type repeating earthquake shown here is these circles, and general seismicity, the repeating earthquakes are the stars, and then general seismicity are the circles, and they're all colored according to time. And the rough location of the top of the subducted seamount is shown here. This is from the seismic profile, but also from magnetic data. Down dip of that is this high reflectivity zone, which are possibly these fluid-enriched sediments. And we noticed that a lot of the burst type repeating earthquake activity is in the upper, appears to be in the upper plate, potentially in like a fracture zone that was likely created from just the seamount subducting. And what we think happened is that during the large plate boundary slow slip event, there was fracturing into the upper plate, which allowed for fluids to migrate from this potentially overpressurized region into likely multiple faults in the upper plate, which didn't change pore fluid pressures, likely allowed for slow slip, which then drove these burst type repeating earthquakes, general seismicity, as well as the tremor. So to kind of summarize that, at the seamount, at the subducted seamount, towards the end and after this slow slip event, there are burst type repeating earthquakes, there's tremor and increase in microseismicity, and combined, we think this is strong evidence of transient slow slip here after the main slow slip event. Now, after the study, of course, one of the questions we had was, well, was this unique to the 2014 event, right? Does this happen every time there's a slow slip event, or was there something special about this event? And, oh, I should actually, sorry, go to my implications. But basically, seamount subduction plays a key role in the generation of shallow slow slip and microseismicity at the Pickering margin. And it looks like burst type repeating earthquakes are a promising proxy for a transient slow slip that's not necessarily related to afterslip. So we didn't have a large earthquake that triggered, transient slow slip and then drove these burst type repeating earthquakes. Okay, so one thing I wanted to show was that we had questions of whether or not this happens during multiple slow slip events or just in 2014. And luckily there was another OBS deployment near the subducted seamount, shown here as these blue inverted triangles. And so luckily, the data was shared with us, and we were able to look for earthquakes, at least before, during, and after a slow slip event that occurred between March and April 2019. And so I don't have the contours of slow slip shown here, but I know that Catherine Woods made a beautiful time-dependent inversion of the slow slip event that I'm really excited to look more at AGU. But right now, we at least know the timing towards the end of March through April, there was a slow slip event here. And so we looked for earthquakes from March to April. and in this box shown here, and then ran these all as templates to look for, if there's any burst type repeating earthquake activity. And these haven't been relocated yet. We're still in the process of doing that. So the general locations are okay, depths aren't that great, but the stars here are what we have found in terms of burst type repeating earthquakes, and they're mostly, towards the end of this slow slip event. So pretty similar. We haven't looked through the entire year yet, but we have a pretty similar result that mostly after the slow slip event concentrated at the seamount, we have these burst type repeating earthquakes. So we're doing some more work on that now, and we'll have that ready for AGU. All right, so now moving across the world here, we're on the Anza segment of the San Jacinto Fault Zone in Southern California. And the main questions we're asking here are whether burst type repeating earthquakes can be used to detect and locate transient slow slip in this region. And we also want to know how often moderate sized earthquakes trigger transient slow slip. So here's our study area. We're here in Southern California. Here's the San Jacinto Fault Zone trending kind of northwest throughout our study area. And the study area that we chose is shown with this red dashed line. We chose this just based off of seismicity patterns. And this is the trifurcation area of the San Jacinto Fault, where it splays into three parallel faults: the Buck Ridge Fault in the north, the Clark Fault in the center, and the Coyote Creek Fault in the south. And this area is located just southeast of the Anza seismic gap, which is locked. And so it's in a locking transition, which makes it interesting to study. It's also interesting because there is a discrepancy between the geodetic locking depth at about 10 kilometers and the depth that we see microseismicity, which is down to about 17 kilometers. And one potential explanation for this is from Witowinski in 2009. And the idea is that beneath the locked seismogenic zone and above the ductile crust, there's this region of deep creep that's driving microseismicity. So there's an interesting relationship between seismic and aseismic slip here. So that's one reason we chose this area. Another one is more practical. The instrumentation is great. So there are 4 borehole strain meters shown here as these purple squares that can detect really small strain changes and therefore slow slip transients. There's also an excellent seismic catalog. So the Quake Template Matching, or QTM catalog from Zach Ross, covers this area. And from this catalog, we were able to take template earthquakes, which are shown as these green stars here. Now, there have also been, in the study area from 2010 to 2016, which was our initial kind of time period to study, there were 3 moderate-sized earthquakes. This one on the Coyote Creek Fault occurred in July 2010. It was a magnitude 5.4. There was also one in March 2013 that was magnitude 4.7 on the Buck Ridge Fault. And then June 2016, there was magnitude 5.2 on the Clark Fault. So, this gives us an opportunity to study potentially, slow slip triggered by these events. And we already have evidence that this occurs in the region. So Asaf Imbal in 2017 studied transient slow slip following this event using borehole strain meter data and general seismicity. He was able to actually model a triggered slow slip transient following this. Meng and Peng also did a study between 2000 and 2013 looking at earthquakes above a magnitude 4 and their aftershock patterns, and saw that the aftershock expansion following this event could be consistent with aftershocks being mostly driven by creep. And then this event in 2013, Meng and Peng also studied and saw that these aftershocks could also be consistent with being driven by creep. And there were 2 abstracts in 2013 that just looked at the strain data following this event. And it looked like there were strain changes following this event that could be consistent with a triggered slow slip transient. So our question is, was there a triggered slow slip transient following this event in June 2016? And at the end of our study, there was also this bonus earthquake in April 2020, this magnitude 4.9, also on the Clark Fault. And so we don't have as much detailed analysis for this event, but I'll revisit it at the end. So we're very interested to see if this also triggered a slow slip transient. Okay, so our main goals are to identify new triggered or spontaneous slow slip transients here. There haven't been any spontaneous slow slip transients identified. And we want to see if burst type repeating earthquakes have been associated with previously identified slow slip transients in 2010 and 2013, and any that we newly identified. So to look for repeating earthquakes, we have similar methodology to before. We're just using template matching, using EQ core scan. We selected templates from the QTM catalog that had a magnitude of greater than or equal to 1.5 in our study area from 2010 to 2016. And this was our cutoff just for signal to noise ratio. And we ended up with 1,100 templates. And we used 5-second long templates. And here's an example of a detection here. So you can see most of our templates have the P waves and the S waves. And we're using 4 to 12 stations, but on average, we're using 9 stations. And we use an average correlation in this case of over 0.9 to call something a repeating earthquake detection. Okay, so this slide's mostly just an overview of what I'm going to talk about in detail for the rest of the talk. So just to remind you, we have these 4 moderate-sized local earthquakes in our study region. And on the right here is a time series between 2010 and the end of 2016, with the timing of at least 3 of those events shown at the top. And known or potential slow slip transients are highlighted in gray. I want to first focus, so on the top, I should go over that first. We have general seismicity in our study area from the QTM catalog. This is just daily seismicity. Beneath that in green are the burst type repeating earthquakes that we found during this study in 1-week bends. And then on the bottom here is the strain data from the 4 strain meters and 3 components. So up top is differential shear strain, the middle is aerial strain, and the bottom is engineered shear strain. And this is level 2 corrected strain data, meaning that it's been corrected for static offsets from earthquakes, for example, been corrected for barometric pressure, been corrected for tides, and also long-term trends have been taken out. So I first want to point out previously identified slow slip transients or transient signals. So on the strain data here, you can see that there is this strain change signal across stations and components. And this was following the Elmira-Kukapa earthquake in April of 2010. This was a regional magnitude 7.2 earthquake, and this was studied by Asaf Enbal, as well as this event in July 2010. So following this event, he also saw a strain change signal across stations and components. There's also increase in seismicity, and we find an increase in what I'll show later are these burst type repeating earthquakes following this event. Similarly, for 2013, there's an increase in seismicity, increase in burst type repeating earthquake activity, and strain change signals across stations and components. So what I want to point out here is that we find these burst type repeating earthquakes coincident with previously identified triggered slow slip transients. Now, moving ahead to what we've detected newly in this study, well, following this event, this magnitude 5.2 earthquake in June 2016, similar to 2010 and 2013, there's this increase in seismicity, increase in burst type repeating earthquake activity, and then we have a very nice strain change signal across stations and components. Okay, so we think that this is a newly detected triggered slow slip transient. There's also this time period in 2015 where you have this anomalous rate, of burst type repeating earthquakes far above the background rate. And at the same time, there's a slight increase in general seismicity. But there's not too much going on at the strain, if you look at the strain data, except for this station here, BO87, which I'll show towards the end is actually the closest strain meter to these burst type repeating earthquakes. It's about 3 kilometers away. So we think that this is a small slow slip transient. We don't find it triggering earthquakes. We actually think this is a spontaneous event. Okay, so next I want to go through the previously identified transients and see what we can learn by incorporating our burst type repeating earthquakes. We want to first confirm that we're seeing aseismic slip, especially for the 2013 event that hasn't been studied as much. And we want to see if we can identify where transient slow slip is occurring, because we think that these burst type repeating earthquakes are being driven by slow slip, surrounding slow slip. Okay, so first let's look at the 2010 event. So on this figure, the x-axis is time. This is July of 2010, with the rough timing of the slow slip transient shown here in gray, and the timing of the magnitude 5.4 event shown at the top. Then daily seismicity is shown here in blue, and the stem plot here are the burst type repeating earthquakes that we found. They're colored according to family, and I'm calling them burst type because similar to what we saw in New Zealand, they have variable magnitudes and irregular repeat intervals. They're more consistent with being burst type repeating earthquakes. I've also plotted one or strain data from one station and one component just to show that following this event, there's this nice strain change signal, and all of the strain data is shown down here. If we look at this in map view, here is the 2010 magnitude 5.4 event. Here's the focal mechanism for it. I've also plotted the focal mechanisms of the burst type repeating earthquake families, and they're colored according to the first event in the family relative to this July 7th earthquake with the color scale shown down here. And, we have a lot of the repeating earthquake activity roughly along the strike of the Coyote Creek Fault where the main shock is at. If we look, you can see that more if we look at a fault parallel cross section. And if we were just to look at the burst type repeating earthquakes, we would probably guess that slow slip is occurring about here. And in blue, I have shown the inversion or slow slip distribution from Asaf Imbal's paper where he inverted for this using the strain data, using seismicity and rate and state friction. And it's actually fairly consistent where we would guess, where we would think that slow slip is occurring based on the repeating earthquake. So that is promising. Now jumping ahead to 2013, this is a similar plot as before, but now we're looking at March through June 2013 with the timing of the slow slip transient shown here in gray and the timing of the magnitude 4.7 earthquake at the top. You can see there's a lot of burst type repeating earthquake activity following this event. And here's this nice strain change signal following the earthquake with all of the strain data shown here. And here it is in map view. So this is the magnitude 4.7 earthquake on the Buck Ridge Fault here. These are focal mechanisms of the burst type repeating earthquakes. And if we zoom in, you can see here's the earthquake on the Buck Ridge Fault. And we seem to have a lot of the burst type repeating earthquakes kind of along strike of, the rough strike of the Buck Ridge Fault. So what we did was we took to get the, slip direction and an average magnitude of the slow slip transient, we approximated fault slip using a rectangular Okada dislocation. And we decided to set the strike right along here of, based on the repeating earthquakes to be roughly on the Buck Ridge Fault, and the dip of about 90 degrees that's shown here in this fault perpendicular cross section and kind of coincides with these repeating earthquakes. And we also set the center of the fault plane using the burst type repeating earthquakes. And then we inverted for optimal fault length, fault width, the rake, and the slip using the strain change data at the nearby borehole strain meters. So, we really wanted to see if we can get just general consistency based on where our burst type repeating earthquakes are. If we could model this with just general consistency. And, here are the results. This is the rectangular Okada dislocation we end up with. And in red on this plot are the observations. So these are strain changes rotated to principal components for each station. And in blue is our model. So, they're fairly consistent. So we think that most of the slip is probably on the Buck Ridge Fault, kind of aligned with these burst type repeating earthquakes. But it also appears that, based on where we have these burst type repeating earthquakes on these apparently, these apparently vertical but parallel structures to the Buck Ridge Fault, we think we probably have, minor slow slip on multiple structures. So probably most on the Buck Ridge Fault and then on some minor vertical structures as well. So to summarize that first part, first off, we just have burst type repeating earthquakes that are coincident with these borehole strain meter transients. So we do think we are seeing a seismic slip, and we think that we can now use burst type repeating earthquakes to identify smaller transients that aren't clearly detected on the strain meters. And second, we were able to use burst type repeating earthquakes to really help delineate slow slip. So now we want to apply this later in time to identify additional transients. So first, let's look at the 2016 event. So similar plot to before, now we're from May to the end of August 2016. rough timing of what we think is a slow slip transient shown in gray and the magnitude 5.2 earthquake at the top. And following this event, we have burst type repeating earthquake activity. We also have a very nice strain change signal, and all of the strain data is shown down here. This is actually probably the best strain changes, or the cleanest that we have seen. So we think that this is a newly detected slow slip transient following this earthquake. And in map view, here's the main earthquake, the magnitude 5.2 on the Clark Fault, and these are the focal mechanisms of the burst type repeating earthquakes that also seem to be along the Clark Fault. And so similar to 2013, we wanted to model this. So we set the strike based off of location of the majority of burst type repeaters. Same with the dip. Here's a fault perpendicular cross section. We end up using a 70-degree dip to kind of line up where we see most of the burst type repeaters, and we set the fault center similarly to where we have the majority of our repeating earthquakes. And here's what we end up with for our rectangular Okata dislocation. And on the map is just shown comparison of the observations versus the model. And once again, it's generally consistent. So we think that most of the triggered slow slip is along the Clark Fault, but once again, we think we have slow slip on multiple structures based on where we have additional burst type repeating earthquakes. So probably in the damage zone between the Clark Fault and the Buck Ridge Fault, there's additional minor slow slip. And this ended up being a magnitude 5.6 event, following a 5.2 earthquake. And based on the timing of the burst type repeating earthquakes, it appears that there might also be a northwest migration in slow slip. Okay, so let's go to that 2015 event where we have all of these burst type repeating earthquakes and an increase in seismicity. And at the closest strain meter, we also have the strain change signal. So this box right here is where we have most of those burst type repeating earthquakes that I was just showing. And this station here, BO87, which is 3 kilometers away, is the only station that detects it. And if we zoom in, it looks like most of that activity is on these 2 previously unmapped parallel faults, about maybe 1 kilometer away from each other and perpendicular to the main fault trend in the area. And in cross section, you can see they extend to from about 7 to 9 kilometers depth. Now, we think that these are, these burst type repeating earthquakes and seismicity are driven by slow slip. And part of the reason is that when we sum up the slip of all the seismicity, general seismicity and repeating earthquakes in this box, and then we see what, strain change we would expect at BO87, it's 3 orders of magnitude less than what is actually observed. So we don't think it's just the seismicity here that's causing the strain change on this nearby strain meter. We think that this is driven by slow slip. And we also could not find a triggering earthquake. So we think this was a spontaneous, moderate depth to shallow and small slow slip transient that was detected on the nearest borehole strain meter. All right, and I want to just quickly show this an earthquake that happened in April 2020 when we were mostly finished with our study, but there was a magnitude 4.9 event on the Clark Fault. And so we took templates kind of leading up to the event and for a few weeks after, and they haven't been relocated, so the locations aren't great. We don't have focal mechanisms, so we still wanted to see if we found some burst type repeating earthquake activity, and we do. It's shown as these stars on the map, and you can see them in time. There's a lot of burst type repeating earthquake activity after this magnitude 4.9 event, and here's strain data from just one station, but you can see there's also this nice strain change signal. So we think that this is another triggered slow slip transient following a moderate sized earthquake in our study area. So to kind of summarize our observations, I'm showing this fault perpendicular cross section from A to A prime here. It crosses all 3 faults: the Coyote Creek Fault, Clark Fault, and Buck Ridge Fault. And I have the 4 moderate sized earthquakes shown as these larger focal mechanisms, and the burst type repeating earthquake focal mechanisms are shown here, and also colored according to the event, except for 2020, which we don't have focal mechanisms for, so they're shown as these stars. And then general seismicity are just shown as these dots here. And I also have the what we ended up using for the rectangular Okata dislocations shown here in black for 2016, 2013. And importantly, I've plotted the geodetic locking depth from Lindsay et al. In 2014, which is at about 10.4 kilometers depth. And so what really, sticks out to us is that it appears that we have, transient slow slip shallower than the geodetic locking depth. Seems anywhere from maybe 6 kilometers to about 14, we have transient slow slip. And so we think that there could be more of a transition zone in this area with moderate depth to deep slow slip that's driving a lot of microseismicity. Okay, so to conclude, what we found in this study area, one, we found this newly detected triggered slow slip transients following this 2016 earthquake, as well as one in 2020. We also found the first evidence of a shallow spontaneous transient in 2015, mostly based off of the burst type repeating earthquakes. And these burst type repeating earthquakes, helped identify and delineate slow slip transients. They also helped us to learn that triggered slow slip seems to occur on several fault segments, both on and off of the triggering earthquake faults. And we found, which was very interesting to us, that all earthquakes of magnitude 4.5 in our study area and period triggered deep to moderate depth slow slip transients with moments that were larger than the main shock. So, moderate sized earthquakes triggering slow slip may be common, and just in a lot of areas, we don't have the instrumentation to detect it, or ANZA, which is located in a locking transition, may be unique. Another area where we've seen these, triggered slow slip transients being a similar magnitude to the main shock is in like San Juan Bautista, which is also in a locking transition. Also, burst type repeating earthquakes in this area can be used to detect, locate, and even evaluate geometrical complexities of triggered and spontaneous slow slip transients. And ultimately, our observations support a model where you have a transitional region at the bottom of the seismogenic zone, where you have really heterogeneous frictional properties and potentially frequent slow slip transients that then drive deep microseismicity. That wraps up the second study area, and the main conclusions then of this talk are that we found burst type repeating earthquakes coincident with tremor at the northern Hikurangi margin in New Zealand that we think were driven by transient slow slip that was really triggered by fluids, or at least changes in pore fluid pressure. And we found burst type repeating earthquakes, that were coincident with strain changes on, strain meters near ANZA. So, we think that these are driven by triggered as well as spontaneous slow slip transients. So ultimately, we think that burst type repeating earthquakes, at least in some environments, are another promising way to indirectly detect transient slow slip that can possibly help us improve our understanding of the interplay of seismic and aseismic slip. Thank you.
Awesome. Thanks for that great talk, Heather. So we'll go ahead and take questions. You can feel free to unmute yourself and just ask it out, or raise your hand, whatever you prefer.
Yeah, thanks, Heather. It was a really great talk, a really interesting studies you've done. The California stuff looks really interesting. But of course, I have a question about the New Zealand work.
Yeah.
I wonder if you could go back to the, just wondering about the depths, whether you looked at any of the deeper earthquakes that would have been supposedly in the subducting plate back with the, your published study, I guess. Yeah, so I was looking at that, and there's this kind of sort of parallel to the dashed line. If you go down a little bit, you can kind of see a little, you could think that there's another line just above the circles. And I wondered if you had looked down at any of those deeper ones and, been able to say, oh, there's not repeaters down there, or whether, that's a question. Did you look at any of those deeper ones?
You know what, we did not. And maybe we should go back and look more. We really just looked pretty close to the plate interface, and we didn't look at anything other than these stars shown here. So any of this deeper stuff we didn't look at, but that would probably be, interesting as well.
Yeah, I guess, the plate interface is fairly not uncertain, although I guess the control stuff is pretty good. But yeah, it'll be interesting anyway to see.
Yeah.
Especially if there's California earthquakes, right? If you just get earthquakes anywhere, are there always transients? Is it only because we're just looking at the slow slip? Maybe there's transients for every earthquake everywhere.
Yeah, I mean, that's, the more I've looked at it, that's more of like or at least me and like Susan have been thinking about it. It's like the more we look, we're all, is it just everywhere all the time? Okay. But no, that would be interesting. We didn't initially do that, but that's something we could, go back and do.
Okay, thanks.
Yeah, thank you.
I have a question since we're talking about the New Zealand ones, I think, did you use Don Eberhard Phillips's velocity model for the 2014? Yeah, which isn't well constrained offshore. For the latest events, because that can have a big influence on whether or not these are in the upper plate or the lower plate or the interface. Because I know Kimi Yuki, who's I think on this call, has developed a better velocity model. What are you guys using for the 2019 event?
We haven't relocated them yet, but we were going to use Kimi's model. Yeah, definitely. That's one of the things we're excited about doing, is seeing where these are, having a better idea of where these are located. Because definitely for the 2014, we were limited by that 1D, model offshore that, like you said, isn't very well constrained offshore. So yeah, one of the things I'm hoping to do before EGU is to use Kimi's model and have much better earthquake locations. Yeah, and we want to do it for 2014 also and relocate those, because we're trying to compare what we have in 2014 and 2019.
Mm-hmm. Yeah, and the 2019 event, I mean, you probably know we've got borehole observatories out there. We'll be collecting the data early next year, so we're going to have a much better handle on the evolution of the event offshore, because it's possible that the slow slip event in 2014 could have persisted for longer offshore. It's just detected geodetically onshore, and the seafloor pressure sensor data has a lot of noise, so it's sort of hard to get a real good handle on the temporal evolution just from the seafloor pressure data. But so the 2019 event is going to be interesting. And then Evan Solomon from University of Washington has a bunch of seafloor flow meters out there right now that were there during the 2019 event. So we'll potentially be able to look at fluid flow transients during that event as well. So it's going to be, I think, some interesting data sets coming out to kind of test some of the things about what's driving the burst type repeaters. So
that's really exciting. Yeah, that's great. I'm just writing that down.
Looks like Brandon has his hand raised.
Awesome. Yeah, I have a similar kind of follow up to that. Great talk. I really enjoyed everything. It's fantastic. Yeah, I was wondering, like in California, it seems like the slow slip and seismicity are kind of overlapping both in space and time a bit more. And in New Zealand, you showed that all the earthquakes were happening after the slow slip was over. And there's also a little bit of like a spatial offset. So I was wondering if that is kind of conclusive in your mind that there were fluids that were basically released and migrating along the subduction channel up into this permeable kind of fractured zone in the upper plate, and if that's, if that can explain that delay in spatial offset.
Yeah, great question. So, I mean, I don't know if it's set in my head, but what made the most sense to us was that it was a fluid kind of diffusional timescale, right? That, and like you said, like migrating into this upper plate fracture zone, and then, really driving slow slip, and then in the seismicity. So that made the most sense to us. I should also say that, when we've been thinking, we've looked at a few places for these burst type repeating earthquakes, and we have yet to find them during a large plate interface slow slip event. And where we've found them more are in these maybe less mature faults, right, with a lot more heterogeneity, right? So maybe that's one of the ways that we can get these burst type repeating earthquakes. And so maybe that's why we see them in really near the main triggering earthquakes and at our work in ANZA, right? Kind of like, maybe on the same fault in a different part of it, or really, really closely off the fault. It could be something to do with the frictional properties. But yeah, in New Zealand, we didn't see anything on the main plate interface. It's more after in the upper plate area. And the time scale that made the most, what explained the time scale most was that kind of fluid diffusional scale. But I don't know if that's set in my head as the only way we could get it, but at least for now, that makes the most sense. And I'm really excited to see the data from fluid flow meters, et cetera, from, during the 2019 event.
Thanks. Yeah. So do you think basically these burst type can be used as a reliable proxy if it seems like it depends more on the permeability structure of the upper plate?
Yeah. So I think that, I've gone back and forth on this. I think that they are best for identifying small transients, and whether they're generated, fluid generated, whether the strain transient is from, fluids or it's from aseismic slip. I don't know, I'm kind of agnostic about, but I think they're better for these really smaller strain transients. Yeah, I don't know. Does that answer your question? I'm sorry.
Yeah, that's great. Thanks.
I have a question. Did you obtain or derive the slip amount for each repeating earthquake, so that you can compare the slip amount, and then which is can be comparable with the slip that is with the slow slip when you compare with this?
Yeah, great question. So we did not. So for most of our families, there's maybe a couple, 2, maybe up to like 5, sometimes 7 events, but most of them are maybe 2 or 3 events in a family. And just based on the really, a regular time period and like variable magnitude, we didn't go ahead and compute slip because we weren't really sure if the relationship that you would normally do that for like continual type repeating earthquakes, right? We didn't know if that relationship still held. And if it was worthwhile to do. So we, both based on like we didn't have a lot of events, and based on the uncertainty with whether we're seeing the exact same patch or overlapping or just closely spaced, we didn't do that. But it might be worthwhile to just try it and see what we get, especially comparing it in ANZA to where we have at least a moment, a pretty fairly reliable moment from the slow slip transients.
Yeah. Well, thanks.
Yeah.
Well, the question that I had, because when I see the distribution of the New Zealand case in 2014 and 2019, then it seems from your result in map, then the distribution, the number of repeating earthquakes is substantially lower for 2018 slow slip, even though the slow slip itself is larger with 2018. I think, but slip amount would be
interesting.
So yeah, that's okay.
Yeah.
But just to make sure that the number of repeating earthquakes detected is lower for 2018 slow slip events, right?
I think it's actually a little higher, because right now it's kind of comparable, but also I need to go back and run more templates. I think I was missing a few earthquakes that I thought I had missing data, and so I didn't run a lot of it. So I need to go back, but I think it might be more. I'm yet to confirm it, but it's comparable and might be more.
Okay, thank you.
Yeah. Sorry, I'm just writing this down.
I have a quick question as well. I'm curious as to what's actually slipping in these different cases. It sounds like in California, your thought is that there are additional structures in between main structures and that they're discrete faults. But in the New Zealand case, do you think they're also on discrete upper plate faults, or is it just slipping within the damage zone around the plate boundary, or do you not have the resolution to really differentiate?
I'm not sure I have the resolution to differentiate. I think that they're distinct faults, but just looking at like composite focal mechanisms within families, they're pretty variable. So I don't know. We were hoping to be able to say more about that from the focal mechanisms, but they're pretty variable. So if it's distinct faults, they're pretty different faults. But yeah, at least right now, I don't think we have the resolution. But that's an interesting question that we have as well.
Yeah, great talk. Thanks.
Thank you.
Yeah, and that's another reason to use the more accurate velocity models that are coming out now. So to help get that location better.
Yeah.
I have a question about the ANZA one. So you might have mentioned it and I missed it, but how much of the moment of that transient is actually from your repeating earthquakes and other seismic? Like is the vast seismic or?
Yeah, we think about 1% or less is from seismicity, and the rest is aseismic. Yeah,
Okay.
Great question. I did forget to say that. Yeah, for each of those events.
Okay, glad I wasn't just being clueless.
No, I forgot to say that.
And then the other one, I think particularly for the 2016 event, you were inferring some migration of the ANZA one from the repeating earthquake locations. Is that seeing that migration? Can you see that in the strain meters? Because that's sort of like, seems like a value of strain meters to be able to see because they're so sensitive. Do you see any migration from that, from data?
We didn't see anything obvious, no, in the strain data, unfortunately. Well, let me pull it up here. Yeah, here's the strain data, and we didn't see anything obvious. It's very messy, but we didn't see anything obvious on the strain data. That would be nice though. And I mean the potential temporal migration from the repeaters is, it's not very strong. It's kind of more suggestive, but yeah, it was hard to confirm on the strain data.
Yeah, I guess Noelle's been involved in this. I don't know if she's tried to do any independent modeling of the strain data. I guess that would be one way to that, but I don't know.
Ask her about that. Yeah, I know a lot of our more ambitious models we ended up not going with just from only having the 4 stations, and they were, pretty messy, but might be worth doing in the future.
All right. Well, thanks so much for joining us, Heather. This was a great talk.
Yeah, thank you. Thanks, everyone. Thanks for the questions. Here, I'll stop sharing this.
Yeah, thanks for the talk. That was great.
And I'll send out the recording to you and everyone else. So I'll CC you. So if anyone has any follow-up questions, Heather's email will be on that email. So feel free to hit her up. Right.
Thank you so much.